Good time of day, dear ladies and gentlemen. My name is Aldemjar Kikbayev and I represent the team SoloPlay, and here are other members. There are Biba Salgabayeva, Daria Talasbayeva, Ibrahim Wali, and Anil Trulikul. So without further ado, let's begin our presentation. First of all, allow me to introduce the problem and the challenge we are facing. It's the historical data of the energy demand forecasting issue, where in the first column on the left, we see the date and hourly rate, and on the second one there is an energy demand in megawatts. So based on that data, we will build a model to make our precise predictions. Next, regarding our stats function, there are many key metrics used, such as min, max, standard deviation, median, and mean, but main ones used for the normalization of our data are the mean and standard deviation as a whole. Going into the process of analyzing the data and normalization, we utilize the Gaussian distribution normalization formula, which states that z-score or x-hat for each input here is the difference between sample input and mean divided by two standard deviations. As a mean, we use 29,766, and for standard deviation is 5,850, which in the result gave us output between -1 and 1 overall. As for the network and solver type, for naive networks, result of which we will see in the pre-last slides, we did not utilize any regularization of weight decays, whereas in different networks, we used L2 regularization and added weight decay of 10 to the power of -6. Additionally, the factor for division in naive one was 2, which is commented here, and in div we implemented a factor of 2/3, 4/9, 8/27 for consequent dividing and more accurate results. For both of them, we kicked off forecasting with 4 layers and 1 in-product saturator. For configuration of our naive network, the default settings were the input size as 2, no repeats, weight decay, and its sizes as 16, 32, 64, and 128. On the contrary, in our difference network, 5 repeats, weight decay was added as 10 to the power of -6, and its sizes for 64 and 128 neurons was input size 19. Solver type in both network configs was Atom, our preferred choice, because it's considered to be more deterministic and to be finding often good solutions. With regards to the early stopping, it was enabled in AutoCAD automatically, and its main purpose was to prevent memorizing by taking as a skip of 25 and 20 points to figure out the trend in our loss graphs. First experiment results for naive networks where there is a graph of training and test losses by iteration, and here we see that the test losses are higher than training ones, and it's a bad sign of memorization. Test loss that we got was 0.07, and we believe that it could be significantly improved because here, even scatter plots and all graphs indicate that dispersion of trained model and lag not equal to 0. One of the techniques we used to upgrade the training network for better forecasting was a number of iterations. As we can see, more iterations were made, but the training was because here, unlike on the previous graph, was test loss less than training one. Next thing to implement here are dropout probabilities. Here we took 0.05, 0.1, and 0.25 and 0.05 worked out the best for us in terms of range of losses that we found quite good. As for the network size, 128 neurons trained better judging by these two ranges out of 16, 32, 64, and 128 perceptrons. Following the advice of our instructors, we use regularization as the method to further improve our model. And here as default, we set the 1 to L2 type because we take squares of all values, not just ordinary values, which makes it more precise and accurate. Lambdas are weight decays, and part of regularization technique which we set to 10 to the power of -6 in order to arrive at the best result there is for our model. Speaking of results, finally, we achieved test loss of 0.00430, which surpasses our persistence almost 10,000 times. Our test and training loss graphs look smooth, and this means deliberate decrease in both characteristics and means successful learning of our model. Graphs of both training and test predictions have lines of actual and prediction coinciding with each other. That means that the experiment was successful. Interesting fact, the data is seasonal and the model can demonstrate its predictions. We see better results of scatter plots since points are mostly focused in a single line movement. The lag this time is 0 for both train and test. While the final experiment showed impressive development compared to the first one, we firmly believe that the model can always be improved. For example, We try using other saturators such as hyperbolic tangent and leaky ReLU, and add more data for a more complete model, such as about 50 or more columns of data. Third is to try a small dropout probability at 0.01. And that will be all, and thank you for your attention.